Hi, and welcome to Everything Embedded. In this episode, we're going to be going over the schematic design for a test fixture to test out this board. So this board is an ultrasonic processing board, and so it's got a SPI connector over here and two connectors for transducers. So this one's the transmit and this one here is the receive. We need to program these at manufacture. And on the back side, there are 5 pins that also correspond to the pins on the connector on the top side. And with these, we can use a little pogo pin, which are these little pins that you can solder into a board and they have a spring inside them. So what you can do is basically have these pins butt up against the back side and make contact on the back. And so somebody can really quickly just plop one of these boards down, hit a button and program it, and load the configuration into it. There's also some pins on the back sides of these two connectors, and we want access to those as well so we can make sure that the signals coming out and going in are what they should be. So for that, they make a similar little pogo pin, except for it has a little cone inside it that's really good at mounting onto through-hole pins like this. So now that we're here in KiCAD, the first thing we're going to do is create a sheet that we are going to put the pogo pins onto. So go grab the hierarchical sheet, grab this, and this will be the ultrasonic pins, and we'll create that sheet, and we will double click on it to go down into it. So for our ultrasonics, we're going to have actually 2 different spots we can plug ultrasonics into this. We have 2 different frequencies, and we use different pin patterns on the bottom to prevent them from getting mixed up during manufacturing. So we're going to need 5 pins for the SPI for one frequency, 5 pins for the SPI for another frequency, and then we're going to need 8 pins for the transducers. So we're going to start adding our pogos. So I've got this pogo pin symbol here, and I'm going to put the 5 of those. I'm going to hit X to mirror it over and drop the 5 down for our power, ground, and the SPI interface. And then I'm going to go put the 4 for the transducer interface. So between these, on the TX side and the RX side, being an ultrasonic sensor, this sends out a really high voltage pulse here and then receives back an extremely low voltage pulse over here. So we need some attenuation in between that. So I'm going to use some resistors in kind of a cascaded divider fashion to bring that voltage down. So I'm going to start with a 1 mega ohm is going to go across the top. And we're going to have 3 of these. And then we're going to use some 10Ks going down to ground. And I'll go ahead and hook these up. And then we need to hook up our grounds. So hit the P key, bring up our power symbols, and grab a ground symbol here. And hook up our ground pins. Now, one of the things I'm interested in is using our microcontroller that we're going to have to measure the voltage here as this is running, so we can tell, like, if we have a problem with one, we can see, oh, did it transmit or is the receive side broken? One of the issues we have, however, is that this is going to be an AC signal here, and it's going to be above and below ground. So to bring this signal up and kind of reference it above ground, we're going to use an op amp kind of in a unity gain configuration. The other thing, I'm not sure which one of these 2 points I'm going to pull from, so I'm going to bring these together with a 0 ohm resistor off to where our op amp input's going to be. So to start with here, I'll grab an R0. So this will be just a jumper resistor we can place to figure out which one we want to use. And then now we need the input to our op amp. So the way to do this is to capacitively couple this. So I'm going to use a capacitor in here. This one's an 0603, so that'll give us room in case we need to change to like a different value or something like that. So we're going to put that here, and then we'll have some resistors that help reference the signal. So for that, I'm going to grab our 10K ohm resistors again. And those will go up to power and down to ground. And then I need a power, which for power, I just like to use global labels in KiCAD. I think they work a little better than the power symbols. They're easier when you need to have a lot of voltages around. So I just use a label. And we'll hook that up. So now this blocks the DC, and this will hold this point at 2.5 volts. And plus, this signal can then swing it through the capacitor, since the AC signal will pass through the capacitor, and this can move relative to that. So now we need to place an op amp. And so this one's a dual channel op amp. So I'm going to place the channel one here, and then I'm going to place the other channel off here, and the power symbol for it as well down there. So we're just going to kind of put those out of the way for now. I'm going to flip this part over so the minus pole's on the bottom. And I'm probably going to run this at unity gain, but in case we need some gain from this op amp, I'm going to set up a little feedback network here so that we have that option. And so for that, I'm just going to place another resistor footprint down here, and then a small capacitor footprint symbol down below as well. So for capacitors, I'm just going to grab a capacitor, it's no 402, and drop that here, and that'll let us adjust anything if we need to. So to hook all this up, the input goes into the positive input of the op amp. We have our output connects here, and the feedback path. And then this connects down to ground. By no placing these two here and just leaving this as a 0 ohm, we'll get a unity gain amplifier, which I think is what we want. If we need anything more than that, we can always tweak some values in here. And so this will be the output to our microcontroller input. And I'm going to go through and just tidy this up a little bit and move and shift it around so we've got a little more space. And then we will copy it to create the second channel. All right, so I got these kind of separated out, went through and cleaned up the text on a bunch of these and kind of scooched things together a little bit just so we've got a little more space on the page. And now I'm going to go and duplicate this and use it to make the other channel. So Control D, and that will duplicate it. I need to switch this out because I need it to use the B package of this guy. And I need to make sure to flip him correctly because we had flipped him vertically last time. So make sure the minus is connected where it should and the plus is connected where it should. I'm going to move this guy out of the way. And I can go drop this guy right down here. So this will make our two different channels of that. And I'll copy the pogo pins over. These I'm going to mirror over, and we'll see why that is in a sec. And I'm going to put the power down here at the bottom. So for the power, we can get that hooked up. So we've got V plus here. The shutdown, we actually don't need to connect on this. It's got to pull up internally, so it'll just leave it on. So I'll add a no connection flag. And we'll add a ground marker down here. The other thing we're going to need here for sure is a decoupling cap on our amplifier. So I'll go just grab this 0.1 microfarad cap. A trick here is if you're placing the ground markers or these power symbols, if you place them right on and then drag it out, it'll automatically create a wire, which can help speed up drawing your schematic quite a bit. So there we've got decoupling on this, and our amplifier circuit's all hooked up. So the next thing we need to take into account is these pins are going to be exposed. They're going to be handled a lot because they're kind of sticking up out of the board. This will be hopefully in an ESD safe manufacturing environment. There's also the risk of like this 8.2, the input to these is 8.2 volts. There's a very good chance that 8.2 volts on a board, since this is a test fixture, we don't know if these boards are good or not that are being tested. there's a good chance that like 8.2 volts could short out to one of these pins here, and we don't want that to damage this test board. So we're going to do a couple different things for some input protection on this. So the first one is we're going to put some ESD diodes. We're actually just going to tie these together as well to start with, because these are all the same bus. So I need to make this will be a 8V2, and we're going to have ground. And let's line this guy up. And something got messed up there. There we go. Duplicate, hit X to flip, and we will drop this right there, and that'll be connected. So I can go through, connect these through. We've got our grounds hooked up and our 8 volts. So the first thing I want to put is some ESD protection on these. So that way, if anything zaps them, doesn't end up hurting anything else on the board. And for that, we have these, since we could have these shorted out to a somewhat high voltage, I'm using one that's 12 volt capable. In case it shorts to 8 volt, it doesn't short through this ESD diode. And then these are dual package, so we'll be able to do 2 signals per diode here. And before I place the others, I'm going to rearrange the text on these a little bit just to shrink them down. And I think I'm also going to move these in a ways to get them out of the way, because I do want to put ESD protection on the 8 volts as well. So if I put this here, I'll be able to run pin 1 to the 8 volts, pin 2 to this line, and then I can copy this across. So I'd like this part to fit a little better, so I'm going to go tweak this part so that the text is a little smaller on it. So I'll go into our symbol editor, and I'm going to grab this text and just make it 30 mils, and then I'm just going to scooch all of it in a little tighter. And that should give me a little more room to place stuff. So I'll save that, come back over here, and then I can go update symbol, so it'll grab the latest from the library. And I want to update all of them matching that library ID since I've got 2 placed. And we will update the field sizes and styles and positions. Click update, and that did not work. Let me see if adding a new one works. There's some settings. Yeah, adding a new one works. Not sure why updating didn't work there. So we're just going to delete these 2. There we go. And duplicate this one over. So this one will connect to these 2 lines. And with ESD diodes like this, you need them really close to the connectors. So we're going to put a second set over on the other side. So I will just copy these and move them over here. And we'll hook these up the same way. Hook that up right there. The next piece I need to pull out of here, and I think I need to make a little more room, so I'm going to try and scooch this guy down just a little bit to buy some room on the bottom here, is I need to pull these signals out, and then we need to add that protection so that if we hook them up to, if they short to the 8 volts, we don't kill these lines. We want to limit these lines to 3.3 volts. And so to do that, what we're going to use is a resistor and a Zener diode. I'll go ahead and grab my Zener diode, which is this guy. So this is a 3.43 and a 400 milliwatt diode, so it can actually take quite a bit of current through it. So that should give us some pretty good protection. And we're going to we need 3 of these. And just gonna get my text rotated into place here. And so these are all going to pull, we'll shunt anything down to ground that's above their Zener voltage. So we need to hook them to ground. And then what we can do is add some series resistors on these signals. So I'm going to go in and grab in my resistor library here. I have a 470 ohm 0603 package. So this should be just about right. We can show you the math and a little bit about how this actually works. But I can place, I'll place 1, and then we'll get everything rotated into place. I ended up changing my mind, decided to go vertical on these, so I got that switched over. So this first one, I want to go up to what'll be this line. Second one's going to go here. Third one's going to go here. And then now I can move these diodes underneath. Put those there. There's not really a great place for these, but I think we're going to be okay. I'm going to add some labels for our sheet here because I need to hook up to these. So we're going to have a SPI clock, which will be an input to this sheet. So this will be out, which is actually out from the perspective of this board. It will be in from the perspective of the ultrasonic. So this is which is an input into here. This gets a little complicated. I'm going to rename this one, just make it SCK. And then we will add a SDI. And that one will be an output. And we're going to scooch these just a little bit. We got a little more room here. And now we can get this wired up. So this is going to go through as the clock. That was not a good way to do that. I need to flip these. Let's do that. Okay, this one's going to go through as the clock on the bottom here. This one's going to go as SDO. And this one will go as SDI. Which I think I can make this just a little cleaner if I scooch this over. Connect that. Connect that, and connect that. So now we're protected in the event of any overvoltage because these Zeners will make sure that the voltage on these lines is not over the 3.43 volts that they will clamp to, and the resistors will limit the current flow in case of a short circuit through this. Okay, so I've gone through and done a bit of cleanup and labeling. So I got our bus labeled up here. I got the pins swapped around here, so these are correct for the pin names. And I kind of drew some boxes around all the important pieces and put some labels on all of them. So here we've got the 48 kilohertz SPI pogos, transducer loopback, and then we can see we have the transducer loopback and the SPI pogos for the 58 kilohertz. We have some short circuit protection with our Zeners, and we have the op amp power. I did realize I'm missing the sheet output from here on these op amps, so I do need to add some pins for that. So I'll go here. This is supposed to be the 48 TX out. So this will be the transmit signal, and this will be an output out of this. And we'll put that here and hook that up. Scooch that just a little bit so he's all inside. And we'll duplicate that and put one over here, and this will be for the 58 kilohertz. And I'm just going to scooch this line out so we're not overlapping. And with that, I think that covers this sheet. So here as kind of an overview again, we've got our SPI hookups here that'll go to our pogo pins. We put some ESD protection on, so they'll be protected from handling. We won't kill any pins on our test fixture. We put some short circuit protection in case any of the SPI pins get shorted to 8.2 volts. We won't break anything. And then we did a little loopback circuit here. So we've got a way for the signal to go from the transmit to the receive. And then within that, there's a little voltage attenuator here. We can pick which tap off of that we want to feed into our op amp. And then we'll be able to listen to that signal out. And we repeated that over here for the 58 kilohertz. And so these are basically identical circuits. So the last thing we need to do here before we're finished with this sheet is to get these pins out into our top level. So we've got these 3 and these 2 that go up to the top level sheet. So we will leave the sheet and then we can grab the import hierarchical sheet pin here. And as we click on these, it will give us a little place to put these. So we do the TX out, we can do our clock, our SDO, our SDI, and the TX out for that one. So that places all of our pins. So now we can hook up our other symbols to those. The next thing we're going to add, now we need our microcontroller. And for this, I'm actually going to use the Raspberry Pi Pico because it comes with a little solder down module. It already has the USB connection and the bypass caps and flash and a bunch of things that we're going to need for this. If this was like a high volume thing, that's probably not what my choice would be. But for a little programming fixture like this, it can be super convenient because it already has a lot of what we need. So I can grab my RPi Pico module here. And we're going to place that down onto the board. And this is pretty easy. We can now go and hook up some of our signals through here. Kind of shift some things around to make them line up. It looks like we have the RX, which is going to be the SDI, needs to be on top. So we'll move that up. The clock's in the middle and the TX that'll be here. So just to make this a little easier to work with, we're going to move these around to be in the right order. And I don't need a big gap between these, so we're going to put them pretty close to each other. So we'll go ahead, hook that up, hook up our clock. We're not using a chip select for this, so we're just going to hook up the SDI here. And go ahead and save that. We also need to get the TX out from these hooked up. For that, I'm going to end up using a label. So this will be the ADC 0. And we'll put that, whoops, I don't think that label is what I wanted. That's going to be an input label. And this one will be ADC 1. And now I can just hook directly to these and then duplicate these labels so I don't have to go around the backside to wire these all the way over. So I don't like using labels a ton. I think they make schematics generally kind of hard to follow. If you can hook it up with a trace, it's usually better. But for things like this, where I'm not using a ton of them, a couple labels can help clean this up so we don't have kind of a spaghetti mess with our setup here. I just remembered as I was looking at this that we didn't quite do the power right on these op amps. I don't actually want to bias this up to 5 volts. I want this to be split between the 3.3 volt rail and ground because our ADC inputs can only take 3.3 volts. So I just need to flip these to be 3.3 volt inputs there. And then the power here for the op amp should also be 3.3 volts. Okay, so we got that fixed. One of the things that's important for power on this Pico is there's a few different ways you can hook up power. So V-bus is the 5 volts that comes right off the USB, and that's what we're going to be using to power all of our rails, or our 5 volts in our system. If you have a secondary power source, like let's say you can plug it in via USB and you also have a battery, they provide this V-sys, and these are connected internally on the RPi Pico with a Schottky diode so that V-sys will not backdrive the V-bus. For our application, we're not going to power anything separately through vSys. So to avoid the voltage drop across that diode, we can actually just short across that, and that's totally fine as long as you're only using the VBus as your main power input. We'll also be using the 3v3 out. That's what's going to provide our 3.3 volt rail for our main board. So I'm going to put a 3v3 label on that. And that'll go right there. The 3.3 volt enable, we don't need to do. We're not disabling this anywhere, so that's fine. And other stuff, we don't need to hook up the VREF. We're going to use the internal. We do need to hook up some grounds, so I'm going to go grab a ground symbol. And for this, I like to hook. There we go. Get exit out. I like to hook up the top one, and then just go through here. Missed on that one, but just duplicate this down. There's plenty of different ways to do this. I find this way works pretty quick. There, so all of our grounds are hooked up. It's important to get all these hooked up. They have them spaced kind of in between the pins. Those will serve as your return paths. So if you don't have those between, if you miss hooking up a ground or something, you could definitely run into some EMI issues if that was a concern. Next thing to add here, we're going to add a little tiny display. This will be kind of cool. It's a little OLED I2C display. So it's got just clock, data, ground, and VCC. And we should be able to kind of hook this up. These are pretty cheap. You can get them off Amazon. But we're just going to hook one of these up to display like error codes and other stuff out of this for letting the operator know if it's working or not. So this guy just needs our 3.3 volt up here. Grab a ground here. One of the things with I2C is, well, most devices that you buy as like dev boards and stuff like that usually come with pull-up resistors. In case I need to adjust them, I like to put some spots to have my own pull-up resistors. So we're going to just grab some little 10K resistors here. And in case we need to adjust the pull-up, we can always populate these or not, kind of depending on what we need out of this. So I'm just gonna clean these up a little bit, and these will pull up to 3.3, and they'll be listed as no place on the bill of materials when I put that together. So we won't place them unless we need them, but it's far better to have the pads to put them there in case we do end up needing them. It's basically some cheap insurance in case we have some I2C problems. So we'll place those. So now we've got a display with our I2C hooked up. Next thing I need access to on the Raspberry Pi Pico is some debug. So they provide an SWDIO, SW clock. There's the run/reset pin and a couple UART pins here. And so those can be super handy if we need to actually like step through our code in a debugger, or for some development, it's handy to, you can get logging and that sort of stuff out of these. So we're going to place a debug connector that works with the high-speed debug probe that I have. And so this uses a 14-pin connector. We're not going to use all 14 pins because this connector also supports JTAG and some other protocols and stuff. But we can pretty easily go ahead and hook this up. So we missed by just one spot there. So we'll have, actually I need to leave some room as well. We're going to put an ESD protection device on this as well. So I'll make sure I've got just a little bit of room since it'll be an exposed header. It's always good to protect those interfaces. So the reset goes to the run pin, and then the TX here goes to the TX here. I have all these pins labeled correctly when we run a design rule check, so this should tell us if we're driving things the wrong way. But I believe I've got the TX and RXs right. Okay, so that guy's placed. I guess we just need to hook up some ground signals on it. We're not going to bother with the ground detect. I don't think my probe actually cares. And we don't need the VCC or any of the reserved. So we can just go ahead and mark all of those as no connects. So we're not using the SWO pin. Those guys are reserved. We're not using the JTAG clock or the JTAG TDI, and we're not using the ground connect. So we just have a UART interface, the reset, the serial wire, debug, IO, and the clock right here. So next we need some ESD protection on this. And so for that, I've got a little multi-channel ESD protection diode that we can drop down here. And we need ground on this guy as well. We're just going to pull this down a couple more and wire these all through here. And then we're going to go wire these up. So SWDIO gets one, clock gets one, reset pin gets one, RX and the TX, and then channel 8 will just be open here, or I guess channel 6, pin 8. So we don't need that one. And so that has us all hooked up for being able to debug the Pi Pico. The next piece we need is some I/O for the technician. So we need some buttons so that they can start programming for each of the two sockets. And then we need some LEDs to tell us if it either passed or failed. So for that, we'll start with the LEDs. So I've got a red LED here. So we can go ahead and place one of those. And then I've got a green one. And then we need a button. So I've got a switch here. We also are going to need some current limiting for our LEDs. So we need a resistor. For that, usually something in the neighborhood of like 330 ohms. Should work pretty good. So I got a 330 ohm 0402 resistor here. Go ahead, place that. And we'll duplicate that. We're going to need two of these. And then these will hook up to some GPIO pins up here. And we need our 3.3 volts to power this. This button needs to be tied to ground. So we'll grab a ground signal. We're going to use an onboard pull-up, so we don't need any sort of pull-up resistor on the board. We'll use the one that's on the microcontroller. And then we'll just have to hook these up. Before I run the wires to hook this up, I'm going to just move this up a little bit so it's a little closer to where we need it and kind of scooch some things in a little bit. Pull that a little tighter. And pull that in. And then I'm also going to get, I say we like to draw a box around things, helps keep our schematic kind of neat and segmented. So we're going to do that here. Make sure to finish and put some text. So this will be the 48 kilohertz user I/O. Oops, make that text a little bigger so it stands out. Easier to find. And now let's just shrink this a little bit. Okay, and then we'll just duplicate this whole box, and then we'll select the pieces inside it, and if we hit X, it will flip it, and we'll kind of reposition it just a little bit within the box and rename this. This will be for the 58 kilohertz. And now we can go run these wires up to our microcontroller. So we'll start with probably this guy here. I'm gonna come out, go up, and I'll start with, we'll start kind of up here towards the top. I'm gonna go to 9. And things are getting a little tight in here, so I'm just going to pull this out. Oop, not like that. And that'll give us just the space we need to get this guy poked through. And then what's very important here, this is kind of hard to read, so we've got to go ahead and put some labels onto these. It'll also make it easier during layout for kind of identifying what is what. So we know this top one is the red LED, so this will be the 48 red. And then we can go tack these labels on there. So that one's the 48 red. This one is the 48 green. This one will be the 48 button. And then this one should be the 58 button. I believe we'll double check. Yep, that's the button. Then we have the green for the 58. And we have the 58 kilohertz red. So that'll make sure when we're in layout, we kind of can tell what's what, because all the nets will be labeled. It would also probably be a good idea with a button like this where the user's finger could be near it to add some ESD protection as well. So I'm going to go ahead and use the same ESD diodes that we used here. These aren't ideal because the clamping voltage is a little high for what we're trying to do, but they'll work for what we need. So I'm just going to put this here, and we can just hook this right up here. So that'll at least give us some level of ESD protection. It's probably not ideal, but better than nothing. The next component we're going to add is our voltage regulator to step up to the 8.2 volts that we need for the ultrasonics. We've only got 5 volts in on the USB here. So for that, we're going to use a TPS 61046. And this is a pretty simple regulator. It doesn't require a whole lot of external circuitry. We just need an inductor and a couple resistors and some input capacitors. So I'm going to put this, I think, kind of over here on the side. We don't need its own page for it. It's not going to be a very big circuit. And we'll grab our input. So we're going to have 5 volts in on this, which I need to actually make and tie to this VSys. So we're going to have 5 volts as our input. I'm going to leave a little space that we can hang some capacitors off of it. The enable pin we're going to hook up to one of the GPIO over here. So I'll make a label for that. Copy this, hook this up to a GPIO pin here. We need to hook up ground. Actually, I need to give a little more space here. Grab a ground. And we need an inductor, which for that I've picked out this little part from Coilcraft. It's a 10 microhenry 1.2 amp inductor. It looks like I've got some visibility of some fields. It's not quite right. I definitely don't need the price or the full part number visible. And I'm going to shrink this guy down just so he's not taking up as much space. There we go. And so for a boost regulator like this, the inductor actually ends up going between V-in and the switch node. This regulator is pretty cool. It has the diode internal, and then it also has overcurrent protection in here too. Typically with a normal boost regulator topology, if you short the output to ground, you actually just short from 5 volts through your inductor, and you can burn up your inductor or cause other bad things to happen. So you usually need some other protection on them. The enable pin doesn't actually turn off the output. But with this one has a switch internally, so it can actually turn off the output, which is really handy for our application because we need to turn the output off. So then over here, we need a output. So that's going to be our 8V2. Tie that up there. And for our feedback network, we're going to have a 93.1K and a 10K resistor. So I'll grab the 93, and this one's going to be the top leg, which I don't really have enough room for, so we're going to kind of tweak it in here. And we'll go our 10K. And then the bottom side of this gets tied to ground. That'll go there. And we need some capacitors. So I've got some 4.7 microfarad 16 volt capacitors. We're going to use one of these on the input. We don't need a ton of capacitance on the input. And then I'm going to put a spot for 4 of them on the output. This is probably overkill. I may not place all of these, but I'd like to at least have the room for them. And if we don't end up needing them, that's fine. This isn't really a space-constrained design. This regulator doesn't need quite this much, but it does want at least a few microfarads on the output. And since these are only 16-volt capacitors, they do get derated quite a bit. So each of these effective capacitance is probably somewhere between like 1 and 2 microfarad. I'd have to double-check the data sheet to be exactly sure. But they're probably less than 60% of their rated capacitance for sure out at 8.2 volts for this package size, which I think these are, yeah, these are only 0603s, so the DC bias derating is going to be rather high on them. On the 5 volts, that's a little less of a problem, and we don't actually need as much capacitance on the input either, so we can get away with just one of them. And so that basically takes care of this regulator. That's all we need. So we've got input capacitance, goes to the switch and the VIN are tied together with a 10 microhenry inductor. The current rating of this inductor is above the overcurrent protection limit of this regulator, which is pretty important. We've got our feedback network set here, and we've got a bunch of output capacitors. I went ahead and did a little cleanup and got a box drawn around this. And there's one last thing I want to implement on this. It's really handy when you're testing circuit boards or other things during production to have a way to measure the current. The current is a really good indicator of certain faults. It can help diagnose or troubleshoot what's going on with a board. And so we're going to add a current sense resistor and a little current sense amplifier that we can feed into the analog pin of the Raspberry Pi Pico, and that'll allow us to measure the current. We'll also be able to detect short circuit conditions, and if something is going wrong, we will know in the code and we can turn off the regulator, turn off power, and mark it as a failed board. To get started here, I'm going to grab our power pin and move this over, and we're going to put a resistor in the path here. And for this, I think a 200 milliohm resistor is going to work about right for the current I'm expecting through here. And this will just get wired in line here. In order to measure the voltage across this sense resistor, we need an amplifier, and there's special amplifiers called current sense amplifiers that are designed specifically for this purpose, where they can be on a high voltage rail, or at least a relatively high voltage rail, and they have kind of set gains and out of the box are really well suited for measuring currents across sense resistors. So I have this INA 18OB, and this is as simple as putting it on here and adding a wire on each side of the sense resistor and connecting the output to our analog input. So this is clear when we're doing layout. I'm going to go ahead and add a label onto this net. So this will be the iSense. And I just need to hook up power and ground. So I need our 3.3 volt power. I'm also going to want a bypass capacitor to go with it. So I'm just going to copy all this down here. We'll put the capacitor here, duplicate the power, duplicate the ground, and wire these in. And that will take care of being able to sense our current. I'll go ahead and get a box drawn around this to keep our schematic neat and tidy. And put some text in here. All right, so that just about does it. I've gone through and done a little bit of cleanup, added some labels to a few things, but I think that is everything we need on this schematic. The only other stuff that I'm not going to show, I usually put things like mounting holes and the fiducials on the schematic, just so I know they end up on the layout and won't get lost along the way. So I'll go ahead and add some of those mechanical pieces, but otherwise this is pretty much done. So just as a little review, we've got our Raspberry Pi Pico. We've got a debug connector for it, so we can talk to it with a programmer in case we need to do some debugging. We have a little OLED LCD display. We have a sheet for our ultrasonics that we'll go into. We've got some buttons and LEDs here, as well as ESD protection on the buttons. We've got our 8.2 volt regulator and some current sense for that regulator. And then on the page here with the ultrasonic pogos, we've got our pogos for the SPI interface for both these, as well as some loopback circuitry so that we can do loopback tests on these, and some op amps to help do a little signal conditioning, change the levels of our loopback test. So that's going to be all for this episode. Please like and subscribe. If you've got any questions or things you want me to cover, leave a comment down below. And in the next episode, we'll be going through how to lay this out.